If I ask you what 50 plus 30 is, you're going to say 80, and in almost every classroom in the world, you'd be right. But let's look at this equation. 50 plus 30 equals 70. This happens because ribosomes, the tiny protein factories inside living cells, defies standard arithmetic. Take a look at this model of a prokaryotic ribosome. It pulls apart into two distinct pieces, a large subunit labeled 50S and a small subunit labeled 30S. That S stands for Svedberg unit. It's highly tempting to treat this as a measure of mass or weight, but if you put these subunits on a tiny scale, they wouldn't weigh 50 and 30. Instead, a Svedberg unit measures a sedimentation rate. When a biologist puts these particles into a laboratory centrifuge and spins them, the S value tells us exactly how fast they sink to the bottom of the tube. Mastering this math depends on analyzing velocity and fluid dynamics instead of mass. Let's visualize this with a macro world analogy. On the left, we drop a compact rock into a column of water. On the right, we drop a large porous sponge. The rock plummets, but the sponge takes its time. The sponge's physical shape creates drag. Even if it has the exact same mass as the rock, that wide, porous surface area pushes against the water, significantly slowing its descent. This exact physical principle applies to the Svedberg unit. A ribosome's sinking speed is dictated heavily by its shape-shifting profile as it moves through the fluid. So an S number is a combined measurement. It accounts for a particle's physical size and the specific frictional drag generated by its exact physical shape. Let's bring this back to our prokaryotic ribosome. When a cell needs to build a protein, the 50S large subunit and the 30S small subunit dock together to form a functional whole. Look at what happens to their geometry when they join. The two pieces interlock, creating a completely new surface area profile. They cooperate structurally, that this new combined shape catches the fluid differently. It generates proportionally more drag than you would get by just adding the separate speeds of the individual pieces moving alone. Because the fluid resistance on this interlocked shape slows its overall velocity, the final sinking speed is exactly 70S. Now let's pivot to human biology. Our cells use a larger eukaryotic ribosome, built from a 60S large subunit and a 40S small subunit. So what happens when they dock? Apply the rule of interlocking drag we just covered. We know that standard addition gives us 100, and we know that standard addition will fail. Take a second to predict the combined S value. When the 60S and 40S subunits snap together, their combined sedimentation rate is 80S. Biological additivity fails here for the exact same reason. The physical interlocking of the two subunits alters the friction, slowing them down as they move through the fluid. Let's lock this in with a quick cheat sheet. The most critical takeaway is that the S stands for Svedberg, which measures sinking speed, not weight. This gives us the two counterintuitive equations you need to memorize. For prokaryotes, 50S plus 30S equals 70S. And for eukaryotes, 60S plus 40S equals 80S. In biological math, subunits physically cooperate, altering how their combined structure